let us now introduce ourselves to the concept of characteristic signal of a linear system and the concept of system function. We will consider a linear time invariant constant parameter, that is time invariant or constant parameter mean one is the same, continuous time system. So, linear constant parameter continuous time system. We have an input quantity x of t and an output quantity y of t. An electrical network consisting of RLC elements being a specific example of this. In general, the output yt and the input xt are connected by a linear differential equation with constant coefficients. Let us assume that the differential equation connecting these two is of this form: a n dny dtn plus a n minus 1 dn minus 1 y dtn minus 1 and so on and so forth, plus a naught y equals dm x dtm plus bm minus 1, you can put bm if you like, bm minus 1 dm minus 1 x dtm minus 1, so on and so forth, plus b naught x. So, this is a nth order differential equation connecting the output quantity y with the input quantity x. Now, the particular integral solution of this is given by the operator bm dm plus bm minus 1 dm minus 1 down the line to b naught divided by a n dn plus a n minus 1 dn minus 1, so on, plus a naught. This is a operator, a function of d operating on x of t. So, depending upon the input quantity, you can calculate the particular integral solution for this. This is what we do in the case of solution of the differential equations. And the electrical network which we considered in the last lecture is a specific example. You remember that we ended up with a second order differential equation from which we can calculate the particular integral solution in the same manner as here. Now, it turns out that if the input function is of a particular type, exponential function a e to the power of st, then the particular integral solution is this operator operating on a e to the power of st. And from the theory of differential equations, whenever you have an exponential function here, this operator function can be thought of as an algebraic function where d is replaced by a particular value of s. So, it turns out that the particular integral solution will be bm s to the power of m plus bm minus 1 s to the power of m minus 1 down the line to b naught divided by a n s to the power of n, a n minus 1 s to the power of n minus 1 up to a naught times x of t, which is a e to the power of st. So, the solution for this differential equation, the particular integral solution, all you have to do is substitute s for d. So, if x is a e to the power of st, ypi is some quantity times a e to the power of st. We often call this hfs, a e to the power of st. So, the particular integral solution, a function of time, is hs times a e to the power of st or hs times xt, when xt equals a e to the power of st. So, this is a very interesting property that the time function describing the first part of the solution and the excitation have got the same function of time, except that is multiplied by hfs, which is independent of time. So, we can think of this as a proportionality factor. This is a function of only s, but not a function of time. So, the input time function and the output time function as far as the particular integral solution are concerned, they are exactly the same, except that it is scaled down by a factor or scaled up by a factor h of s. So, where the input excitation function and the output function have the same form of time function, it is said to be a characteristic signal of a system. The characteristic signal are sometimes called eigen system, eigen function, characteristic function or characteristic signal are also called eigen signal. Again, the meaning of an eigen signal or characteristic signal is, it is that particular signal which, if it is given as input, the output will also have the same time variation except for a scale factor, and that scale factor is h of s in this case. So, e to the power of st is a characteristic signal, e to the power of st with a constant multiplier, any constant, is a characteristic signal of linear time invariant continuous time systems. This is a very important property. Any linear time invariant continuous time system will have this as characteristic signal, and therefore, if the input is in that form, the output is obtained by merely multiplying this by h of s, where h of s is a kind of proportionality factor. And this h of s is called the system function. And in describing the characteristic signal, s can be complex, s need not be real, it can be need not be imagined, it can be complex in general. Therefore, a complex exponential signal of this type, a e to the power of st, mathematically a can be complex as well. Therefore, a e to the power of st is a characteristic signal, and the complex frequency associated with this signal is s. And the system function, which represents the proportionality constant between the output and the input, is called the system function. It is a function of the complex frequency of the characteristic signal e to the power of st. This is called a system function, and this will be the form bm s to the power of m plus b naught divided by an s to the power of n down the line to a naught. So, if you know the differential equation, then the system function can be easily be obtained. After all, you have got bm s to the power of m, bm minus 1, the same coefficients appear in the two polynomials constituting the rational function h of s. So, this system function is a rational function for lumped parameter systems which we are dealing with. Rational function means it is a ratio of two polynomials, and for linear lumped parameter systems, system function turns out to be a rational function, is a ratio of two polynomials. If I call this g of s over f of s, g and s are two polynomials, and these two polynomials are easily set up. If you look at the differential equations, the coefficients in the differential equation constitute the constants in these two polynomials. So, and further, it is, since it is a rational function of a complex frequency variable s, two polynomials, we also would find it useful to represent this in this manner, some constant m times s minus z1, s minus z2, so on. Since this is an nth order polynomial, you have s minus zn divided by s minus p1, s minus p2, and so on, s minus pn. So, you can factorize the numerator and denominator in this form, and the set of values are called the zeros of f. These are the values of s which make h of s 0, go to 0. If s is equal to z1 or z2 or whatever it is, the h of s becomes 0. That is why they are called the zeros of h of s. The set of values of p which make the denominator vanish are called poles of h of s. These are terms which some of you may be familiar with from your study of complex variable theory. So, in any case at the frequencies of S, at S values of S which correspond to a pole of HFS becomes infinitely large, it blows up. That means the denominator is made equal to 0. On the other hand, if S equal to Zi, any I equals 1 to m, then the system function becomes 0. These are usually represented in the complex plane by the 0 locations are given like this and the pole locations are given by crosses. So, these represent poles and the zeros are represented by small zeros. Since these are values are in general are complex, then they can be represented in the complex plane. This is called the S plane or complex plane, and the values of the zeros and poles are represented in this fashion. And you recall that whenever these coefficients are all real, whenever there is a complex pole, it is accompanied by its conjugate. Whenever there is a complex zero, it is accompanied by its conjugate. So, they appear in pairs. Of course, as far as real zeros and real poles are concerned, they can appear of a unit order singly without any second pole or zero appearing as a conjugate, because that zero or pole is itself by itself real. There is no necessity for a conjugate pole or zero to appear since they are real. Now, system function plays a very important role in linear system studies, as we will see later, and particularly when you take up Laplace transform techniques. This system function is a very important tool in our analysis of linear systems, but it has nothing to do with Laplace transforms really. It is we can regard this as the ratio of the forced response to the excitation when the excitation is of the form a e to the power of st. That is all we need to know about it. So, what we have seen now is that if we are talking about a linear time invariant continuous time system represented by this black box with an output and an input xt and yt, then the forced response of the system, instead of particular integral solution I am calling YFS, that is forced response, is HFS times xt if xt is a characteristic signal. This is the summary of what we have discussed just now. This proportionality is valid only when xt is of the form a e to the power of st, not for other signals. That is important. And secondly, we saw that HFS is the ratio of two polynomials in S, g of s over f of s. And if you look at the way in which we calculated g of s and f of s, we took the operator function giving the particular integral solution and formed f of s and g of s. F of s equals a n s to the power of n, a n minus 1 s to the power of n minus 1, and so on and so forth. So, f of s equal to 0 is the characteristic equation. That is the characteristic equation from the differential equation. That is what is called the auxiliary equation. So, the zeros of roots of this equation which are the same as poles of HFS. We said poles of HFS are the zeros of f of s, are the roots of the equation f of s equals 0. So, the roots of f of s equals 0, that equation, which are can be called also zeros of f of s. The roots of the equation f s equals 0 can be termed as zeros of f of s, values of s which makes f of s 0, which are also the poles of h of s. These are give the natural frequencies of the system. What is meant by natural frequencies? These are the frequencies present in the complementary solution or the homogeneous differential equation solution. So, this HFS builds in itself a lot of properties. Not only it gives the forced response for this type of excitation, but it also gives you the form of the complementary solution straight away. So, whatever information is available in the differential equation is built in this system function. Once you have the system function, you do not have to look at the differential equation again, because all the information that is available in the differential equation is given here, because from this you can set up the differential equation if you wish. Now, but you do not even have to do it, because the complementary solution, if you want, all you have to do is solve for fs equal to 0, that equation. It gives you all the terms that are present in the natural part of the solution or the complementary solution. In special cases, it often turns out that we would like to have xt of the form e to the power of j omega t. This is a special case of xt being e to the power of st. If xt is e to the power of j omega t, that means we are taking s equals j omega, in which case the forced response will be h instead of s, it is j omega times x of t, where xt is e to the power of j omega t. Now, this is important because whenever we are talking about sinusoidal quantities as the excitations or inputs, sin omega t, cos omega t, they can be related to the e to the power of j omega t. For example, cos omega t can be thought of as a real part of e to the power of j omega t. Alternately, you can think of this as the sum of two exponential functions, as I already mentioned earlier. Similarly, sin omega t can be regarded as the imaginary part of e to the power of j omega t, or the combination of two characteristic signals like this. So, e to the power of j omega t is closely related to the sinusoidal functions, which we are very important in system studies, and therefore, the response of a system to the signal of e to the power of j omega t can be regarded as a special case of the response to an exponential signal e to the power of st. After all, e to the power of st and e to the power of j omega t are closely related. So, this is also important, and when we study later on Fourier transform methods and Fourier series methods, h of j omega becomes very important, and this h of j omega is itself sometimes called system function, but more commonly we can call it the frequency response function. Frequency response function. Also, sometimes when there is no scope for confusion, this is also called system function. So, this is very important, that is h of j omega is also regarded as system function or a frequency response function. This is a special case of h of s where s is equal to j omega, and this becomes very important when we analyze any system on the basis of sinusoidal inputs, because e to the power of j omega is as good as cos omega t or sin omega t as far as analysis is concerned. We then before we move on to other topics, let us see what kind of system function you have when we have discrete time systems. As an example, let us take a second order discrete time system. B naught xn. Now, this is a second order discrete time linear constant parameter discrete time system. What we have studied earlier is a continuous time system, this is a discrete time system. It can be shown that xn equals some constant times Zn is a characteristic signal. So, just like e to the power of st being a characteristic signal for this continuous time domain, in the case of discrete time system, a e to the power of a times z to the power of n is a characteristic signal. A is a multiplying constant, we can disregard that. Z to the power of n is a characteristic signal, and the forced response y n, the particular integral solution for y n, can be written as b2 z squared plus b1 z plus b naught divided by a2 z squared plus a1 z plus a naught multiplied by x of n, when x of n is a characteristic signal. So, if x of n is a characteristic signal, the forced response of the second order discrete time signal will be b2 z squared plus b1 z plus b naught by a2 z squared plus a1 z plus a naught, just in the same way as we had in the continuous case. From these coefficients you form these two polynomials, and this we will write this h of z, where h of z is, of course, once again xn is a characteristic signal, is to the power of n, and h of z is called again system function in this case. So, this is a discrete time system function, which is a function of z, h of z, just like h of s, you have got h of z here, and the working is quite analogous to the continuous time case. The characteristic signal is z to the power of n instead of e to the power of st, and the system function is h of z instead of h of s, but z is the polynomial, z is the variable that you get in this. We will deal with this later at the end of the course when we deal with discrete time systems. So, this is a parallel development as applicable to discrete time systems. It completely follows the same lines that we have for the continuous time system. So far we have talked about three different ways of characterizing a linear system. What are the different ways? Let us see what they are. So far we have discussed different ways of dealing with linear systems. Let us see what they are, recapitulate what they are. One is the differential equations. Solution of the differential equations will give us the transient solution. We saw the difficulties associated with this. Second method is system function h of s. You can use the system function, it gives the same information as the differential equation h of s. Then we also saw an equivalent is the frequency response function. H of j omega. It turns out that when we later on study Laplace transformation methods, the system function comes into its own. We will try to exploit the properties of the system function to deal with the transients, and when we study later the Fourier transform methods, we will use the frequency response function h of j omega. There is also a fourth way of describing the system response. This is called the impulse response. So, if you give an impulse to a system, the input is an impulse, the output we call it impulse response, unit impulse, this is h of t. This is an independent way of characterizing a system. All are equivalent. That is, if you know the system function h of s, you will be able to analyze find out the response for any given excitation. Similarly, if you know the frequency response function h of j omega, you should be able to find out the response to any excitation. And likewise, an impulse response h of t is also an independent way of characterizing a linear system. If you know the response to an impulse, you should be able to find out the response to any given input x of t. And that is also an independent way of doing this. There is yet another way, what is called the step response. So, here you are giving u of t unit step as the input, and what you get is the output at, that is the step response. These are all different ways of characterizing a linear system, and all are equivalent. Each will give complete information about the system which you need to solve for the response under any given excitation. We have studied the differential equation to some extent, and we will leave it at that. We have noted the methodology that is involved, and we also noted some of the difficulties. The difficulties will be overcome when you use the system function approach using the Laplace transformation methods, which we will take up at some point later point in this course. And we will also study how to exploit the information that is available in h of j omega, the frequency response function, when we study Fourier series and Fourier integral methods. But we do not have to go to this complex frequency or the frequency omega. We can carry out the work in time domain using the impulse response or the step response. They are independent ways of characterizing the input output relations of a linear system, and this is something which we will look up, we will examine in some detail in the next lecture. But we will use this information again further when we go to Laplace transformation methods. We will see how the h of s system function and the impulse response h of t, how they are closely related to each other. That will be taken up at a later point of time. But in the next lecture we would have a closer look at the impulse response method of characterizing a linear system.